Hi, today we're going to look at some acid-base reactions, and specifically we're going to start with an organic acid reacting with a strong base. So when I get an equation like this, the first thing I always want to look for is reactive functional groups. So here I notice that there is a carboxylic acid, and over here I notice that I have a strong base. So I want to recall what I know about acids. Acids have protons that they like to donate. Bases have hydroxides that like to accept protons. Okay, I should also be able to remember that if I have a proton and a hydroxide, those are going to combine and they are going to give me water. I'm going to take the H and it's going to bond with the OH, and one of my products is water. The other product is made up of all of the leftovers of this reaction. So first I'm going to go ahead and copy what's left of the carboxylic acid. And I see that everything is intact, except I've lost that H. When you lose a proton, you leave behind a negative charge. So I have what we would call a carboxylate ion. And then what's left of the base is the sodium ion. So those two combine together, and I end up with water and then a salt over here. This salt, incidentally, is special. When you have a long fatty acid that combines with strong base, this salt is called a soap. Now, just to add one more thing on here, soaps dissolve in water, whereas the original long-chain carboxylic acid would not dissolve in water. If a water molecule is found near this soap, water has dipoles where the protons end up with a partial, or the hydrogens end up with a partial positive, and the ion in the soap ends up attracted to that partial positive. And what I see between the soap and water is an ion dipole attraction. Pardon my awesome writing. So over here I'm looking at an attraction between the negative ion on the soap and the partial positive on the hydrogen. So that was an acid reacting with a base. Next we're going to look at an organic base reacting with acid. So looking at the chemicals here, I want to find the reactive functional groups. So I see here's a heteroatom, a nitrogen, which is different from all the carbons. And then over here I identify a strong acid, which is going to be a donor of protons. So bases I know accept protons. Acids I know donate protons. So we're going to see a movement of this proton from the acid onto the base, because nitrogen has that lone pair of electrons that is ready to be an acceptor for the proton. So here's the product that I get. As you can see, a proton moved over, bringing with it a positive charge, and then what was left of the hydrochloric acid was a Cl-, which will be present there as well. What we call this is a protonated amine. In other words, an amine that has accepted a proton. And just like we saw with the long-chain fatty acid on the previous slide, once you turn it into an ion, it suddenly becomes more water-soluble. And this is also a case where now that I've made it into an ion, if a water molecule comes by, the partially negative O will be attracted by an ion dipole attraction to that positive charge that's on the amine, and you end up with a higher water solubility. So that wraps up our acid-base reactions for organic acids and bases.